Hello everyone, this is Devarpan. Today we will be covering the part 1 of the tutorial on diffusion models that are already covered as part of the theory classes. Today we will be going through the first part of diffusion model, which is primarily focused on the forward process of diffusion, and the backward diffusion process will be covered in the next tutorial on diffusion models. So let us get started. So coming to the diffusion models, the intuition and the forward process specifically, this tutorial covers primarily the lectures that are covered in week 7, and the hands-on material covers the primary questions about diffusion models, that are why diffusion models, forward diffusion by adding Gaussian noise. It covers the linear and cosine variance schedules of the noise addition to the signal or the image, the denoising intuition, Markov chain interpretation of diffusion process, closed form sampling at any time step and how it compares to the iterative process, signal to noise ratio, noise prediction objective, and training a small time step conditioned CNN on the MNIST dataset. Okay. Coming to the learning objective of the diffusion model. Here is a set of imports that you need to perform, and then setting the device to GPU and making torch related imports and so on. Coming to the intuition of diffusion model, a diffusion model separates generation into two processes. First is the forward process, which starts with the original image denoted as x0 or original signal, and then in iterative process x1, x2 and so on till xt, it converts it to a Gaussian noise in small steps. Small amount of Gaussian noise are added, and in the reverse process you intend to start with xt, which is a normalized Gaussian noise, and then you intend to come back or predict the original image that x0 is. So, a neural network is required to learn the reverse diffusion process, that is x3 from xt to x0. So, coming to the forward transition as we talked about. So, Q distribution, which is distribution of next step given the previous step, that is Q xt given xt minus 1, that is Gaussian with mean of square root of 1 minus beta t times xt minus 1 and variance of beta t times the identity matrix, that is the covariance matrix. So, this how this came and derivation of this was covered as part of the theory. Now, you define alpha t as 1 minus beta t, and you can define alpha t bar as pi of like multiplication of all alpha s till that step, and then any noisy state you can sample, which is denoted as xt as, and there is a closed form expression that you can derive, which is square root of alpha t bar x0 plus square root of 1 minus alpha t bar times epsilon. That is the expression of any intermediate step of the diffusion process with respect to the original signal we started with, that is x0. Okay. Now, coming to the variance schedules, that as you have noticed, we start with the original image and go to a Gaussian noise. Now, these steps can be varied in a linear or a nonlinear fashion. So, we discuss one of the two most widely used variance schedules, which is linear, which is simple, versus the cosine schedule, right. So, let us start with t, let us set t equal to 1000, that is 1000 number of steps will be there starting from the original image to the noisy image, Gaussian noise, and you can define the linear beta schedule or a cosine derived beta schedule which are implemented. Yeah. Now, you can see that both ranges starting and end points are same, it goes from 0 to 1. Okay. and now you can essentially plot these schedules, and you can see how these steps varies. You can see that the linear beta stays same from the starting time step to end time step. It stays uniform to 1 upon 1000 obviously, and the cosine beta, it starts with a smaller value and then slowly increases with the increasing time steps. Yeah. Okay. Now you can essentially also plot the SNR, that is what is the fraction of original signal that is retained when you start from that starting time step and the original image or original signal and slowly go towards the Gaussian noise. You can see that because cosine takes smaller steps initially and then suddenly increases the steps. So, cosine schedule has a so compared to linear, cosine has a more uniform decline of the fraction of the original signal. That is why cosine is preferred. Although linear takes uniform steps across the time stamps, so it has a initially slowly degrading signal and then it suddenly degrades, whereas cosine has a more uniform rate of decline. So, what is the quantity of the original image that remains is defined by the alpha t bar that we defined earlier. Now, let us examine the forward diffusion process and implement it on a real image. Okay. So, we take a image, we simply load an image using SK image, an astronaut image which is commonly used in these experiments you might have seen, and if you display the image it looks like this. Yeah, that is the original image, and you can now timestamp specific coefficients you need to calculate, as we have defined already the alpha and betas. So, you define extract function which takes values, time steps and target step, and you also define a function called q sample which samples a noisy image directly from the qxt given x0. So, this is the marginal distribution of any intermediate step given the original image or original signal. Okay. Now, for just visualization we need to see how the intermediate steps look like. We define these visual time steps as some intermediate steps like 0th, 50th, 100th like that till 999 which is the last. Okay. Now, if you try to visualize it, it looks like this. You start with the 0th timestamp and then you go to 999 timestamp, and you can see that the image slowly converts to the Gaussian noise at the end of the process, and intermediate steps are kind of like the image slowly getting more noisier and noisier. Now, you can also visualize how these two different variance schedulers which are like linear and cosine schedulers different from each other. So, in the first row you can see that initially the image gets suddenly so noisy, and within 500 timestamp it is almost like close to the Gaussian noise, whereas as we had shown you through the graph or plot before that the original image slowly decline into a Gaussian noise in more uniform fashion in the cosine scheduler, cosine variance schedule. That visualization you can see in the bottom row where the image much more uniformly converts to the Gaussian noise. Okay. Now comes a very important part of it, part of diffusion model's forward process, which is Markov chain interpretation. The forward diffusion process can be interpreted as a Markov chain. What do you mean by Markov chain? So, Markov chain has this property that the next step only depends on the previous step. So, this is an important interpretation of forward diffusion process, that to get the next noisier image you only need the previous noisier image. Okay. So, just to define mathematically, the distribution, marginal distribution of xt given xt minus 1, xt minus 2 till x0, that is nothing but q of xt given xt minus 1. So, given xt minus 1, to get the distribution of xt, you do not need xt minus 2 till x 0 anymore. Once xt minus is known, you can get the distribution of xt. So, let us implement the Markov forward transitions using beta t and alpha t formulations that we already had shown the formulation for, and here is a visualization of the Markov process. So, you start with t equal to 0 and t equal to 999, and then you can see that similarly this similar to what our forward diffusion process is supposed to give. Similarly, this image slowly gets converted to the Gaussian noise. Now the important question you will have is how they compare, right. So, we had a closed form expression of q xt minus 1 given x 0, and you had a forward diffusion process based on that. But then based on the Markov chain interpretation of the diffusion process, you can also get a original image to noise conversion steps. Now, how they differ from each other? What is the variance? So, we essentially take the iterative and direct methods generally produce different individual samples because they are different random draws. They nevertheless represent the same marginal distribution. The following Monte Carlo experiment compares their empirical mean and standard deviation. So, we define the clean signal, which is x 0, which is simply a scalar, let us take, and then you define the target timestamp to 500, number of samples to be 20,000, iterative process you can define and compare the closed form versus the iterative process of using Markov chain. So, you can see that the mean and standard deviation that are obtained are pretty close to each other. That validates our previous theoretical finding and understanding that Markov chain modeling is enough when you do closed form sampling in forward diffusion process. Now, you can define signal to noise ratio defined as alpha t bar divided by 1 minus alpha t bar at time step t. So, signal to noise ratio should be high at the initial step because there is only signal and no noise, and as you go forward and you signal reduces and noise increases. So, SNR should go down, and at the final step there is only noise, there is no signal. So, if you plot it, you can see that actually happens. Both in case of linear and cosine schedule, the SNR monotonically keeps decreasing. Only variance is how they decreases. Another limitation of the linear scheduler, which was much simpler, but we saw some limitation of it earlier, and here is another, that it does not degrade your SNR to that low value where cosine scheduler can degrade the process to. So, ideally our desired process is that SNR should be as high as possible at the starting and it should be as low as possible at the end. So, cosine schedule gives a much better range from that aspect. And here we come to the noise prediction objective, which is an important part of the next part, which is reverse diffusion process. So, we ask this question that you have a clean image x 0 and you have random time step t, and you sample the Gaussian noise epsilon, and you constructed x t, which is an intermediate tth step of the forward diffusion process. Now, given x t and t to a neural network, can you predict the noise epsilon? Because this is not a linear process and you need to use a neural network, but can it predict it? Can it predict the noise given these arguments? So, the simplified objective that you essentially use as a training objective or loss to minimize it using gradient descent is expectation of epsilon minus epsilon theta. So, epsilon theta represents the neural network parameters. So, you essentially are trying to learn an epsilon using a neural network theta given the arguments x t and t. Can you predict epsilon? So, squared error between them. and you train a simple MNIST noise predictor using it. Okay. So, you define the transforms and train test splits on that, and you just obtain the train and test data for your neural network training. Training examples are 12,000 and validation examples are 2,000. And here is set of clean MNIST training images which we use to create the data set. And we define a CNN which takes the images as image and tries to predict the noise as we have already defined. So, we define the neural network for that, and here are the number of parameters, which is like 1,24,000 order parameters, and then you define the batches and enable the training for it and the evaluation function. Yeah. So, what you obtain is that the mean squared error that we already defined as L simple keeps reducing with the training steps, and validation MSE also reduces. And what you observe is that the mean square error keeps reducing with more optimization steps. That means that shows that you can quite well approximate the noise given the arguments of time step and the xt, x0 and t. So let us assume that you have predicted the noise quite well, that is epsilon hat theta xtt is a very good approximation of epsilon that you have already done. So under that assumption you should be able to reconstruct your original image. So that is a cross validation of how your training is apart from the loss, which is a crude way of measuring. So if you have predicted the noise well, then if you subtract that predicted noise from the noisy image, you should get back your original image. So if you try to visualize it, then you can see that this first row and last row compares. So first row were the original images and last row are the reconstructed images by subtracting the learned noise. You can see that this was a very small scale implementation of it, this and also one iteration of it. Actual reverse diffusion process will use lot many steps and will have much more predictive power, but you can approximately see that you kind of get back your original images, although not of great quality, but here was just a toy example of how this works, how this concept works. We will go into this much deeper in the next part of diffusion model. A decreasing noise prediction loss does not mean that the model can already generate high quality images that you can see, and a complete DDPM will still actually require reverse process equations, iterative sampling rather than this one step solution, and a stronger UNet architecture rather than a simple CNN, longer training, and optionally some conditioning and guidance, which we will discuss in the next part of the tutorial. Yeah. So they will be taken care, and in case you want to get your hands dirty further on this and feel looks interesting to you, here are a couple of exercises I have noted down for your own exploration. Okay, so I will finish this today's tutorial with just a summary. Forward diffusion gradually destroys the image structure with Gaussian noise. This process is Markovian. A variance schedule determines how rapidly the signal is removed. Yeah, and the closed form equation enables efficient random time step training. The signal to noise ratio decreases with time step. The network receives both xt and t when it is trying to predict the noise for a particular time step t. A basic DDPM often learns to predict the added Gaussian noise using the MSE error that it tries to minimize using a neural network. Full reverse diffusion will be covered in the next part of the tutorial, and that's it for this tutorial, and thank you.